Okay, hi guys. So in this lecture, we'll be starting off with seeing some rearrangement reaction, and then we'll be seeing the effect of toluene, phthalates, and bromine water on D-glucose and D-fructose. Okay, so let's get started. So we have first some rearrangement which is known as Lowry, De Bruijn, Van Enkenstein rearrangement. Okay, Enkenstein rearrangement. Okay, so let's draw some enolic form of a carbohydrate. Okay, so we'll have something like HCOH double bond COH and then HOH OH here and more OH and finally OH here. Okay, so this is when we pass this into, let's say, a basic medium. Okay, so we get D mannose, and when we pass D mannose into again basic medium, we get D fructose. Obviously this is D glucose. Okay, so we can say that enolic form of D fructose, D mannose and D glucose is same. The reason is pretty straightforward and you can pretty much guess it, because enolic form is only defined by these two carbon atoms. Hence all the enolic form of these three carbohydrates or monosaccharides would be same. Okay, so let's now discuss about the testing of D glucose and D fructose. How do they behave in different reagents like toluenes, phthalates and bromine water. Okay, so both glucose and fructose pass Tollens test because both contains aldehyde group. Similarly, phthalate they would also be passing. Regarding Br2, you can say that only D glucose will be passing and not D fructose. Okay, and why is this the case? Because if you look at the structure of D glucose and D fructose, uh, I would have drawn it here only, but I am drawing it again. Glucose, mannose and fructose structure, I'll draw it again. Okay, so D glucose is something like, by now the structure should be clear to you. At least for D glucose it should be OH on the right, one OH on the left, and then remaining OH, 3 OH on the right. Okay, this is D glucose. And what about D mannose? D mannose would be something like this. Again, only one H is different, rest all are same. Why? Because it is a epimer. Okay, finally OH here. Okay, what about D fructose? D fructose would be something like CH2OH here, and we have got C double bond O here, and then we have got HOH here, and HOH. Finally we have got HOH and OH here. Okay, so this is the structure of D fructose, and I hope you remember that the tolerance and valence test, uh, what will be the nature of the test in all the compounds, and basically we were comparing between glucose and fructose. Okay, so this is a keto group with attached CS2OH group, that's why it is showing tolerance and valence test. Okay, otherwise ketones doesn't show these two tests. And why it is not showing Br2 water test? Because Br2 water we strictly require a aldehyde. Okay, so let's see some more interesting facts. Okay, so this is pretty much what I want to discuss in this lecture. Okay, and now let's see some interesting problems which is based on some concepts or our understanding of previous lectures as well. Okay, so let's get started. So some facts here, that CrO3 and H2SO4 is a strong oxidizing agent. Even if I have not told in the previous lecture, I am telling it now, that CrO3 or H2SO4 is a strong oxidizing agent. And secondly, CrO3 and CH2Cl2 is a weak oxidizing agent. So just a difference of solution in which CrO3 is placed, we get different nature of the same compound, is a weak oxidizing agent. Okay, next we can see that this is an important concept, that when we react, let's say a alkene with the first water, it won't show any reaction. If we reacted with OH minus and water, it won't show any reaction. And if we react with H plus and H2O, then it will show reaction. Why? Because alkene is a nucleophile. Alkene will behave as a nucleophile. It will attack on electrophile, something like H plus in the reaction. Okay, hence it will show reaction here. Okay, so let's discuss some more interesting questions on the same. So this is in general, means these are all the important questions which come to our mind, which have been asked in previous year papers. Okay, so we have something like this, and we have BRH and H here. So what actually happens? Will it have nucleophilic substitution, elimination, nucleophilic addition? This is N here. AC2O and dehydration. This is small d, dehydration. Okay, so yes, it can undergo nucleophilic substitution. Elimination it can undergo. We have Br and H here, they can form a double bond. Will it undergo nucleophilic addition? No. AC2O, no, it's not a alcohol. And will it undergo dehydration? Yes, it can undergo dehydration, or you can say not dehydration, dehydrogenation. Okay, so I'm just replacing it, dehydration, with dehydrogenation here. Dehydrogenation. Okay, let's see this compound, PHCS2OH. We have then this compound, and finally we have Br here and NH2 here. So which of the following compounds will go on nucleophilic substitution? This can go on nucleophilic substitution. This cannot go. this is OH rather. Okay, this is OH. It cannot go undergo nucleophilic substitution. Yes, it can also undergo nucleophilic substitution. Okay, elimination, only this can go. In this, it can't undergo elimination because there is no alpha hydrogen. Phenyl ring we won't be considering for the alpha hydrogen case. Obviously these two will also not go. Nucleophilic addition, no scope here. It can undergo nucleophilic addition here. Okay, CS3 Grignard reagent can be used here, and similarly this will not go nucleophilic addition. AC2O reaction with AC2O, only alcohol groups will go. Alcohol OH groups are present in this and this, hence both will undergo AC2O. Dehydrogenation, so dehydrogenation, this can undergo dehydrogenation. We have H atom here and H atom here. Yes, it can undergo. This can undergo dehydrogenation. We have two hydrogen atoms here. Okay, similarly these two cannot undergo dehydrogenation. Okay, so with this we come to an end of this lecture. In the next lecture we'll be discussing more on ozone formation. Okay, so till then, good luck and goodbye.